Okay, so I was doing this question. I've done it before, but I still got confused about the proof of two-sum to make it. So to do this question, well, essentially we have a list, and we want to find three indices that are different from each other, and the corresponding elements all sum to 0. So the brute force way is to just do for I, for j, for k, and just try all three combinations. There are 3,000 elements, so that's 3,000 cubed. That's in the billion, so don't consider that approach. We need to optimize it a little bit. And if you've done two-sum before, you know one way to make it to make it n squared to linear approach is to sort it and then do a two-pointer approach. So we can keep I as it is, but then we can do a two-pointer approach here for I and j, for j and k, like that. But this only works if the list is sorted. So let's sort this list to something like so -4, -1, -1. We have 0 and 1, 2, and 4. So we start I here, and we can start j here, and for two-pointer we start k at the very end. So as I goes through the list, we start j as I plus 1 and k at the very end of the list. And we search for an element. We want to find a combination of j and k such that the corresponding elements sum to the negative of the element at I. So that means they all sum to 0. So I'm looking for a 4, a combination of two numbers here in this part of the list that sum to 4. And the two-pointer approach is to start like this and then sum up these elements and see what that is. So we have a 3. If we have a 3, we know that that's smaller than our target. We're looking for 4. So the only way to possibly get a 4 is to increase the the left end, which is j. So that's still -3, so it's increased again. We get a 4. Now that's too large. Oh no, that's perfect. So this is the answer. We found a combination of ij and k that equal to 0. But let's say, for example, that this is a 1. So in this case, we have a 5. And this is a 3. Okay, so in this case, we have, we're up to here. If we do it again, we have, this is a 3, and we're looking for a 4, so that's too small. Here we've increased it, and now we get a sum of 5, that's 4 and the 1. That's too large, so in this case, we need to decrement k. Now, you might be asking, like, why doesn't this really work? Why does this really work? So these two elements, we've already figured out that they're too small to get a possible combination, because we've already tried the greatest element combined with these two elements, and we couldn't find anything. So that means we can throw these away, because everything we try in between is going to be smaller than 4. And we can throw away 4 because we know that that element is greater than anything. Than any element here that could make that useful. Hopefully that makes sense. And then we have 3 plus 1 is 4. That's perfect, so that's our answer. So let's give this a go. We start at, first we have to sort the elements. nums.size, nums.begin, nums.end. So once I've sorted it, I want to go through for each I, all the way up to nums.size minus 2 plus I. Why minus 2? Because I only want I to go up to this one here, because that means I can make j equal to this and k equal to this. So this value here at the end is the size minus 1. This one is going to be minus 2. This will be minus 3. So if I want to have I increment as long as it's less than minus 2. That's why I say nums.size minus 2. Alright, so now we do the two-pointer approach, where we start j, so int j is equal to I plus 1, and we also start k at the end. This is not in a for loop though, so we say int j is equal to I plus 1, and we say k is equal to nums.size minus 1, and we do a while loop. So while j is less than k, once they're equal, break, because we don't want j and k to be equal. They all have to be different. First we get the sum, and now if nums at j plus the nums at, okay, it might be worth just like pair sum is equal to nums j plus nums I. Oh, I have to return all triplets. Okay, so I should probably store the answer in a vector of vectors. So I have the sum. If the sum is less than the negative version of nums I, because I'm looking for something that will cancel out nums I. I'm looking for a sum that will cancel out nums I. So I'm looking for something to equal negative nums I. So if the sum is less than negative nums I want to increase it to some value. I want to increase j to increase it. Else, if sum is greater than nums I, minus j, minus k, and else they're equal, so I want to add to the answer. So I want to do answer dot pushback a vector, and this vector will be ijk. And ijk, let's just, I think it doesn't matter what order ijk is like that. And then at the end I return answer. So that should work, hopefully. If I missed something. Okay. Oh, else if they're equal, I should decrement j and k. Oh, and I want to push back the nums. Oh, so many bugs. And I have too many answers as well. Okay. Because I haven't thought this out right. I think the trick is to skip over some of the duplicates. So do this. While. So what's the current j at? So while nums j is equal to current increment j, and also I need to make sure that j is less than k. While k is greater than j and nums at k is equal to current. So int current is equal to nums at k. I need this here as well. Oh, nope, that won't work. Need that here, need this here, like that. Int I is equal to 0. Say while I is this. While I is less than nums.size minus 2 and nums at I is equal to current, then increment I. I think that was the reason why. I is less than nums size minus 1. Solution is way more complicated than I thought. I think because this is an unsigned int, so I have to say int n is equal to nums.size. That's annoying, eh? Should do it? I'm not sure. Yeah, alright. Whatever. It's just... should probably fix that up everywhere. Nice.